Hello and welcome to Earth Analyst. Tonight we will be drifting into what was Earth like during the Paleozoic Era. Sit back and relax, so I can take you on a gentle ride where nothing else matters. The Paleozoic Era was a time unlike anything we could imagine today. An age stretching from about 541 to 252 million years ago, when Earth was undergoing radical transformations in land, sea, and life, and the very foundations of modern ecosystems were being built. It was an era of shifting continents, as ancient landmasses began their slow drift across the globe, colliding, breaking apart, and forming the supercontinents that would shape the future of the planet. The seas were vast and dominant, covering much of Earth's surface, and they were teeming with an explosion of life forms never before seen in the history of our world. Strange and alien creatures ruled the oceans, from trilobites crawling along the seafloor to armored fish and giant cephalopods that filled the waters with predators and prey. The Cambrian explosion at the dawn of this era unleashed a dazzling variety of new body plans, laying the blueprint for nearly every major group of animals alive today. The shallow seas became cradles of biodiversity, with coral reefs beginning to take shape and ecosystems growing more complex with each passing million years. On land, at first, the landscapes were barren, lifeless stretches of rock and sand, silent and empty except for the occasional microbial mats clinging to damp surfaces. But over time, green life crept in, with the first plants pushing upward in damp environments, small and simple at first, but destined to transform the atmosphere and reshape the land. The Silurian and Devonian periods marked the moment plants conquered the continents, carpeting the earth in greenery and releasing oxygen that fueled the rise of new creatures. Forests began to appear, dense and towering, with primitive trees and ferns, creating shade, soil, and a whole new frontier for life to exploit. Insects and arthropods were among the first to explore these new ecosystems, crawling and buzzing in ancient swamps, while fish in the seas began to adapt fins that would one day become limbs. The Devonian is often called the Age of Fishes, for the oceans swarmed with armored placoderms, swift sharks, and the first lobe-finned fish that would crawl toward land. By the Carboniferous Earth was a swampy, humid paradise, with vast coal-forming forests that stretched across continents, breathing out oxygen in such abundance that giant dragonflies and enormous arthropods thrived. The air was thick and rich, allowing life to grow to sizes unimaginable today, and the land rang with the sounds of primitive amphibians that had finally emerged from the water. Amphibians became rulers of the wetlands, bridging the worlds of sea and land, while their descendants would give rise to reptiles with tougher eggs that could survive away from water. The continents of Gondwana, Laurasia, and others shifted ever closer, colliding in massive tectonic upheavals that pushed up mountains and shaped the landscapes that still leave traces today. By the late Paleozoic, the supercontinent Pangaea was beginning to assemble, uniting most of Earth's land into one colossal mass. This colossal reshaping of geography altered climates drastically, from humid equatorial swamps to arid deserts in the continental interiors. Reptiles grew more diverse and more advanced, setting the stage for the great dynasties that would come after them. But the Paleozoic was not only a time of birth and expansion, it was also a time of catastrophic endings. Throughout its span, several mass extinctions swept away entire lineages, reshaping the evolutionary path of life forever. The most devastating came at its close, the Permian-Triassic extinction event, often called the Great Dying, which wiped out more than 90% of marine species and 70% of life on land. It was the deadliest extinction in Earth's history, a grim finale to an era of extraordinary change. Yet, even in its endings, the Paleozoic cleared the way for what was to follow. For from its ashes would rise the Mesozoic, the age of reptiles, and the time of dinosaurs. The Paleozoic was an age of firsts, the first complex animals, the first reefs, the first forests, the first insects, the first amphibians, the first reptiles, and the first steps onto land. It was a time when Earth transformed from a mostly barren, alien-looking planet into one filled with forests, swamps, rivers, and thriving ecosystems. Its seas nurtured biodiversity that set the foundation for life as we know it, while its lands became laboratories for experimentation where plants, animals, and entire ecosystems were born. The skies, once empty, became alive with the flutter of insects, while the land grew lush and green, forever changing the atmosphere of the planet. The oxygen-rich air of the Carboniferous made Earth almost supercharged, fueling evolutionary experiments that would not be possible in our modern world. From trilobites to giant dragonflies, from armored fish to primitive reptiles, the Paleozoic offered a world filled with creatures both bizarre and fascinating. It was also a time when geology and biology intertwined, as shifting plates and colliding continents created new habitats, climates, and evolutionary pressures. Every period within the Paleozoic brought radical changes, each one building upon the last, each one opening doors for new forms of life to take hold. The Cambrian set the stage with the explosion of animal diversity. The Ordovician expanded the seas with reefs and new species, and the Silurian saw the rise of plants and jawed fish. The Devonian brought the first forests and the conquest of land, while the Carboniferous filled Earth with swampy jungles and giant creatures. And the Permian closed the chapter with reptiles and catastrophe. Each transition marked a step forward in the great experiment of evolution, an unfolding story that still echoes in the DNA of every living thing today. The landscapes were alien yet familiar, with mountains rising, forests spreading, and creatures adapting to challenges in ways that still inspire awe. The Paleozoic era was the foundation, the bedrock of life's great expansion, a time when the impossible became possible, when seas became cradles of innovation, and when land became a canvas for life's boldest experiments. The very coal and limestone we mine today were formed from the forests and reefs of this era, a reminder that its legacy still fuels our modern world. Its creatures, though long extinct, left fossils that tell us of their triumphs and struggles, whispering stories of resilience, adaptation, and survival. It was a world of giants and pioneers, of catastrophes and recoveries, of beginnings and endings, a world that would shape everything that followed. The Paleozoic was not just an ancient chapter of Earth, it was the chapter that wrote the rules of life as we know it, and without it, our world would be unrecognizable. It was Earth in transformation, Earth in motion, Earth alive with creativity and destruction, a symphony of evolution that played out over nearly 300 million years. It was the story of a planet learning to breathe, learning to grow forests, learning to build ecosystems, and learning to recover from devastation. The Paleozoic Era stands as a testament to the resilience of life and the ever-changing nature of the Earth itself. It reminds us that the world we live in today, though familiar and stable to us, is only a snapshot in a much larger and far more dynamic story. It shows us that change is the only constant, that life is endlessly adaptable, and that even after the greatest of losses, new beginnings are always possible. When we think of Earth's ancient past, the Paleozoic shines as the time when the planet first became recognizable as the living, breathing world we know. And though its creatures are gone and its forests long turned to stone, the spirit of the Paleozoic still lingers, written in every rock, every fossil, and every living thing. It is the era that built the foundation of life, the blueprint of biodiversity, and the enduring reminder that Earth has always been and always will be a planet of transformation. The dawn of the Paleozoic Era began more than 500 million years ago, and it marked a profound turning point in Earth's history, as life that had once existed only in simple forms suddenly exploded into complexity. At its dawn, the seas were teeming with brand new creatures, from trilobites to early mollusks, and the stage was set for one of the greatest periods of innovation in natural history. This was the time of the Cambrian explosion, when evolution seemed to accelerate, producing a staggering variety of new body plans, many of which still form the foundation of animal groups alive today. The continents were mostly clustered near the equator, their rocky surfaces barren and lifeless, but the shallow seas surrounding them shimmered with biodiversity. The Earth's climate was warm and stable, providing the perfect conditions for life to spread and adapt. As life diversified, the ecosystems grew more intricate, predator and prey interactions emerging for the first time in recorded history. It was a period of experimentation, with nature testing endless forms and strategies for survival. This unfolding drama beneath the waves laid the groundwork for the rich and complex biosphere we recognize in our modern world. The Paleozoic dawn was not quiet but vibrant, alive with the sounds and motions of creatures that had never existed before. It was the first great flowering of animal life, an event that set into motion everything that would follow in the grand saga of Earth. Oceans. Alive with diversity, the seas of the Paleozoic era were nothing short of extraordinary, filled with creatures that would seem alien to our eyes, but formed the foundation of modern marine ecosystems. Trilobites scuttled along the seafloor, while brachiopods and corals anchored themselves, creating the first reef systems. The Ordovician period expanded on the Cambrian explosion, as cephalopods with long, coiled shells became formidable predators. Jawless fish swam in schools, their bodies armored with protective plates, precursors to the vertebrate lineage that would dominate later eras. The ocean was not just a habitat, but a theater of constant evolution, where survival demanded adaptation. Waves of extinction and recovery shaped the marine world, forcing species to innovate or perish. Coral reefs grew in complexity, providing shelter for countless species, while plankton spread widely, forming the basis of ancient food chains. From tiny filter feeders to enormous predators, every niche was explored. These waters were warm, shallow, and often oxygen-rich, ideal nurseries for biodiversity. For nearly 200 million years, the oceans were the beating heart of the Paleozoic world. They were the cradles of experimentation, the centers of innovation, and the places where nature's imagination ran wild. Without these ancient seas, life as we know it today would not exist. The rise of early plants, though the oceans thrived first, it was the conquest of land by plants that reshaped Earth forever during the Paleozoic era. The earliest land surfaces were barren, rocky, and silent, but small, moss-like plants began to creep across damp environments. These pioneers were humble in form, yet monumental in impact, as they transformed lifeless soil into vibrant green landscapes. Over time, vascular plants evolved, with stems and roots that allowed them to grow taller and reach further into the ground for water and nutrients. The Silurian and Devonian periods saw the Earth's first forests beginning to rise, their primitive trees creating shade and shelter. Oxygen released by these plants changed the composition of the atmosphere, raising levels that made it easier for new forms of animal life to breathe. Plants stabilized soils, influenced weather patterns, and gave rise to entirely new ecosystems on land. Their expansion marked the beginning of terrestrial ecosystems, and with them came opportunities for insects and arthropods to colonize the land. The forests of the Devonian were lush and strange, filled with towering club masses and ferns. What began as small green patches grew into sprawling landscapes that covered continents. The rise of plants was not just a step in evolution. It was a revolution that forever altered the Earth's surface and atmosphere. The Age of Fishes, the Devonian period, is often celebrated as the Age of Fishes, a time when the oceans teemed with vertebrates that would become the ancestors of all later fish, amphibians, reptiles, and mammals. Placoderms, armored fish with massive jaws, swam alongside sharks that were among the earliest of their kind. Lobe-finned fish, with their muscular fins, developed structures that would one day give rise to legs, enabling the first creatures to take tentative steps onto land. Coral reefs flourished during this time, creating habitats that attracted a dizzying variety of species. Predators grew larger and more efficient, driving an evolutionary arms race that shaped the development of marine life. The Devonian seas were vibrant and dangerous, alive with swift hunters and armored prey. Meanwhile, freshwater environments also began to diversify, creating opportunities for fish to adapt to rivers and lakes. The evolutionary experiments of this time laid the foundation for the transition of life from water to land. The Age of Fishes was not only about aquatic dominance, but also about setting the stage for the emergence of amphibians and ultimately the conquest of terrestrial environments. It was a period of transition, growth, and bold evolutionary steps that changed the course of history forever. Life steps onto land. The leap from sea to land was one of the most monumental events of the Paleozoic era, and it forever altered the trajectory of life on Earth. Amphibians, descended from lobe-finned fish, were the pioneers of this great transition, adapting their fins into limbs and developing lungs to breathe air. The early terrestrial world was lush with greenery, thanks to the spread of plants, and it provided a new frontier filled with opportunity. These amphibians explored swamps and forests, their bodies still tied to water for breeding, but their mobility granting them access to untapped resources. Insects also began to appear on land, buzzing and crawling among the plants, forming some of the earliest food chains outside the seas. The Carboniferous period especially saw this flourishing of terrestrial life, with ecosystems that looked both alien and familiar. Giant dragonflies soared through the skies, while amphibians grew into diverse and sometimes massive forms. The conquest of land was not easy, requiring countless adaptations, from stronger skeletons to ways of conserving moisture. Yet these creatures persevered, pushing into a world that had once been hostile but was now fertile and green. The moment life walked onto land marked a profound new chapter in Earth's history, one that continues to shape our planet today. Swamps and coal forests. The Carboniferous period was dominated by vast swampy forests that stretched across much of the globe, creating an Earth unlike any we see today. Towering trees, giant ferns, and dense vegetation filled these wetlands, producing oxygen in such abundance that the atmosphere reached levels far higher than in the modern era. This oxygen-rich world allowed arthropods to grow to enormous sizes, with dragonflies as large as seagulls and millipedes stretching several feet in length. Amphibians thrived in this environment, and reptiles began to emerge, their eggs capable of surviving away from water, freeing them from the last tie to the seas. The thick, swampy forests of this time would eventually become the vast coal deposits that fuel modern industry, their remains compressed over millions of years into black rock. These forests not only shaped the climate, but also provided the backdrop for dramatic evolutionary advances. The Earth during this time was humid, warm, and buzzing with life in every corner of its green expanses. The Carboniferous was a world where oxygen filled the air, swamps stretched endlessly, and ecosystems pulsed with energy. It was one of the most unique and vital chapters in Earth's ecological history. The rise of reptiles while amphibians had made the first great strides. Onto land, it was the reptiles that would secure dominance and mark the future of terrestrial life during the late Paleozoic. Reptiles developed the amniotic egg, a remarkable adaptation that freed them from the need to return to water for reproduction. With tough shells and protective membranes, these eggs allowed reptiles to spread across drier and harsher environments. Their bodies were better adapted to conserve water, making them more suited to life on land than their amphibian cousins. By the Permian period, reptiles had diversified into many forms, from small insect eaters to large predators. Some lineages began to resemble the ancestors of future dinosaurs, while others developed traits that hinted at the mammals yet to come. The expansion of reptiles marked a new balance in ecosystems as they competed with amphibians for dominance, and often won. Their ability to thrive in dry, arid regions opened the door to habitats previously uninhabitable. With reptiles, life was no longer bound to the swamps and wetlands. It was spreading across deserts, forests, and plains. Their rise signaled the beginning of a new era where terrestrial life would dominate the Earth for millions of years to come. The assembly of Pangaea, late Paleozoic, was also a time of monumental geological change, as the continents slowly drifted together to form the massive supercontinent Pangaea. This assembly reshaped the face of the Earth, uniting nearly all landmasses into a single colossal block. The collision of continents pushed up mountain ranges, altered ocean currents, and drastically changed climates. Interior regions of Pangaea became dry and arid, far from the moderating influence of the oceans, while coastal areas remained humid and lush. These climatic shifts influenced the evolution of life, forcing species to adapt to harsher, more varied conditions. Pangaea's creation also connected once separated ecosystems, allowing species to migrate and compete across vast new territories. This supercontinent was both a stage of opportunity and a crucible of survival, as only the adaptable could thrive in its extremes. The assembly of Pangaea was a defining event, laying the groundwork for the planetary dynamics that would shape the next era. It was not just a geological transformation, but a biological one, as life adjusted to a world restructured on the grandest of scales. The Great Dying, the end of the Paleozoic Era, was marked by one of the most catastrophic events in Earth's history, the Permian-Triassic extinction, often called the Great Dying. This extinction event wiped out more than 90% of marine species and 70% of terrestrial species, reshaping life on Earth forever. The causes remain debated, but massive volcanic eruptions in Siberia are thought to have played a central role, releasing enormous amounts of carbon dioxide and triggering climate chaos. Temperatures soared, oceans became acidic and oxygen depleted, and ecosystems collapsed under the strain. Coral reefs disappeared, trilobites vanished after flourishing for millions of years, and entire families of animals were lost forever. On land, forests thinned, and many reptile and amphibian groups were driven to extinction. It was the deadliest extinction in Earth's history, a grim ending to an era of extraordinary growth and transformation. Yet, even in its devastation, the Great Dying cleared the way for new beginnings, paving the path for the rise of dinosaurs in the Mesozoic. The end of the Paleozoic reminds us that life is both fragile and resilient, capable of enduring even the darkest chapters of planetary change. Legacy of the Paleozoic Era was more than just an ancient span of time. It was the foundation upon which all later life on Earth was built. It saw the first explosion of animal diversity, the conquest of land by plants and animals, the rise of forests, the emergence of insects, amphibians, and reptiles, and the creation of ecosystems that would echo into the future. Its oceans were cradles of innovation, its swamps were engines of atmosphere change, and its continents were canvases where evolution painted bold new forms. Even its tragedies, the extinctions that punctuated its story, played crucial roles in shaping the path of survival and adaptation. The very coal and limestone we mine today are direct legacies of its forests and reefs, proof that the Paleozoic still powers our world. Fossils from this era tell us stories of resilience, creativity, and the boundless potential of life. Though its creatures are long gone, their imprint remains in every living organism today, a shared ancestry rooted in this transformative age. The Paleozoic was Earth's great experiment, a time of beginnings and endings, of destruction and renewal. Its legacy endures as a reminder that our planet has always been and always will be a place of change, challenge, and infinite possibility. The Cambrian explosion at the very start of the Paleozoic Era. The Cambrian period introduced one of the most astonishing events in the history of life, the Cambrian explosion. In what seems like the blink of an eye on a geological scale, countless new animal groups appeared, each with unique forms and survival strategies. Creatures developed hard shells, exoskeletons, and complex body structures that offered protection and strength. Trilobites became iconic representatives of this time, scuttling across seafloors in staggering numbers, their fossils later forming the backbone of Paleozoic paleontology. Soft-bodied creatures left behind impressions in sediments, evidence of their fleeting existence. The food chains grew more sophisticated, with the first true predators evolving alongside their prey. For the first time, ecosystems resembled the complexity of modern seas, with layers of interactions that gave rise to balance and competition. The Cambrian seas were dazzlingly diverse, with sponges, worms, mollusks, and early chordates among their inhabitants. These organisms were not simply surviving, they were thriving, multiplying, and radiating into new forms with remarkable speed. This burst of biodiversity created a foundation for all future life, ensuring that the Cambrian explosion would forever stand as one of the most pivotal moments in evolutionary history. Ordovician, seas following the Cambrian, the Ordovician period, carried the Paleozoic into a new age of marine dominance, expanding the diversity of life and filling the oceans with extraordinary creatures. Coral reefs became more established, built by organisms that constructed intricate habitats for countless other species. Brachiopods flourished, while nautiloid cephalopods roamed the seas as fearsome hunters, some growing to lengths of several meters. The first true jawless fish appeared, representing the dawn of vertebrates that would later come to dominate Earth. Trilobites remained abundant, but evolved into new and specialized forms, adapting to different ecological niches. Plankton became increasingly significant, forming the basis of thriving food webs that stretched across the oceans. During this time, global seas covered much of the continents, creating shallow marine environments that became hotspots of biodiversity. The Ordovician world, however, was not without its challenges. Toward the end of the period, one of the earliest mass extinctions struck, caused by dramatic climate shifts and glaciation. Yet the Ordovician seas left a lasting legacy, proving that life could not only diversify but also adapt and recover after catastrophe. It was a chapter that deepened the richness of the Paleozoic oceanic story. Silurian stability. The Silurian period brought a measure of stability after the extinction at the end of the Ordovician, allowing life to rebound and explore new evolutionary directions. The climate warmed, glaciers retreated, and sea levels rose, creating fresh habitats across the shallow seas. Coral reefs expanded dramatically, housing diverse communities of fish, mollusks, and other marine creatures. This was also the time when jawed fish first appeared, setting the stage for the incredible evolutionary leaps of the Devonian. On land, the Silurian marked the true beginning of terrestrial ecosystems. Small vascular plants spread widely, creating green patches on the once barren continents. These plants stabilized soils and altered atmospheric conditions, allowing the earliest arthropods, millipedes, scorpions, and insects to make their way onto land. The Silurian was a bridge between the marine-dominated early Paleozoic and the more balanced marine terrestrial world that would follow. It was a period of cautious but steady expansion, where ecosystems grew more resilient, plants and animals forged new paths, and Earth continued to transform into a planet that looked increasingly alive in every direction. Devonian forests. The Devonian was not only the age of fishes, but also the era when forests began to cloak the continents in green, altering the landscape in ways that would endure for millions of years. Early trees, such as Archaeopteris, grew tall, their roots spreading deep into the soil and their branches reaching toward the sky. These forests created shade, generated organic soil layers, and released oxygen that enriched the atmosphere. Insects buzzed among the leaves, while amphibians prowled through the swampy undergrowth. Rivers meandered through these green expanses, carrying nutrients back to the seas. The spread of forests dramatically affected the global climate as plants absorbed carbon dioxide, lowering atmospheric levels and helping to stabilize conditions. Forest ecosystems became the laboratories of evolution, supporting intricate food chains and offering new environments for terrestrial life. These landscapes were alien by modern standards, dominated by strange ferns and club masses rather than flowering plants, but they were vibrant and teeming with possibilities. The Devonian forests marked one of the greatest revolutions in Earth's history, establishing land as a thriving domain for life and forever altering the balance between ocean and continent. Giant insects of the Carboniferous. One of the most striking features of the Carboniferous period was the extraordinary size of insects and arthropods, with atmospheric oxygen levels reaching nearly 35%, far higher than today's 21%. These creatures were able to grow 2 dimensions impossible in the modern world. Dragonflies with wingspans over 2 feet long filled the skies, while millipedes stretched up to 8 feet in length as they crawled through dense undergrowth, creating ecosystems that allowed arthropods to flourish like never before. Amphibians hunted them, while reptiles began to appear as competitors, forming dynamic and active ecosystems. The sheer abundance of oxygen not only affected the size of these creatures, but also influenced fire, making wildfires a regular part of the Carboniferous landscape. These giant insects have captured the imagination of scientists and storytellers alike, serving as reminders of how different Earth once was. The Carboniferous skies and swamps were alive with buzzing, crawling, and fluttering giants, a spectacle that has no equal in today's ecosystems. Amphibian empires. During the Paleozoic, amphibians became some of the most dominant vertebrates on land, particularly during the Carboniferous. Descendants of lobe-finned fish, they had adapted to a dual life, capable of surviving both in water and on land. Amphibians diversified into countless forms, from small insect eaters to massive predators capable of reaching lengths of several meters. They ruled the wetlands, hunting insects and smaller creatures, while serving as prey for larger reptiles as they emerged. The amphibians of this era were far more diverse than those we see today, with body shapes and sizes that reflected a wide range of ecological roles. Their dominance symbolized a transitional world, one still connected to the seas, but increasingly defined by terrestrial ecosystems. Amphibians thrived for tens of millions of years, shaping ecosystems and leaving behind fossil evidence of their sprawling success. They were the bridge between aquatic and terrestrial dominance, the proof that life could leap boldly into new environments and flourish. Reptiles take control as the Paleozoic marched toward its close. Reptiles began to take center stage, gradually replacing amphibians as the dominant land vertebrates. Their secret weapon was the amniotic egg, a protective innovation that freed them from the swamps and allowed them to reproduce in dry environments. With scaly skin that resisted drying and more efficient lungs for breathing, reptiles were well suited to the arid conditions of the late Paleozoic world. By the Permian period, they had diversified into a variety of forms, some resembling early crocodiles, others hinting at the lineage of mammals. Carnivorous reptiles stalked the landscapes, while herbivorous forms grazed on the strange vegetation of the time. This adaptability ensured their survival in ways amphibians could not match. Reptiles pushed into deserts, forests, and plains, steadily expanding their influence. Their rise was a key turning point, setting the stage for the later dominance of dinosaurs and eventually mammals. The reptiles of the late Paleozoic were not yet the giants of the Mesozoic, but they were pioneers of their own, explorers of dry lands and harsh climates, marking a bold new direction in evolutionary history. Shifting climates, the Paleozoic era was not static, but marked by dramatic shifts in climate that reshaped life again and again. These fluctuations drove extinctions, but also spurred adaptation, forcing life to innovate in order to survive. Plants altered the climate as they spread, pulling carbon dioxide from the air and releasing oxygen, creating feedback loops that affected global temperatures. The Carboniferous period saw lush, humid forests, but the assembly of Pangaea in the Permian created vast, arid interiors. Monsoons, deserts, and seasonal climates all emerged, offering new challenges and opportunities. Life followed the rhythms of these climatic changes, with some species vanishing, while others radiated into empty niches. The Paleozoic climate story is a reminder that Earth has always been dynamic, never fixed, and that survival has always depended on resilience and adaptability. These shifting climates forged the evolutionary pathways that shaped not only the Paleozoic, but the future of life itself. Extinctions and recovery. The Paleozoic era was defined not only by its triumphs, but also by the devastating extinctions that periodically swept away entire lineages. Each extinction reshuffled the evolutionary deck, eliminating one successful species and opening opportunities for new ones to rise. The Ordovician-Silurian extinction struck as ice ages and sea level changes wiped out much of marine life. Later, the Devonian extinction eliminated many reef builders and fish species, altering ocean ecosystems dramatically. But the most catastrophic came at the end of the Permian, when the Great Dying decimated the majority of all life. These losses were tragic and immense, but they also paved the way for renewal. After each collapse, ecosystems recovered, often with new dominant groups replacing the old. Evolution moved forward in fits and starts, its progress shaped as much by destruction as by creation. The cycle of extinction and recovery was central to the Paleozoic, underscoring the fragility and resilience of life. Without these events, the trajectory of evolution would have been entirely different, and the world we know today would not exist. The end and a new beginning. The closing chapter of the Paleozoic era was both tragic and transformative. The Permian-Triassic extinction, the deadliest in Earth's history, swept away nearly all life, leaving behind a scarred and empty world. Volcanoes, climate chaos, and oxygen-depleted oceans turned the planet into a hostile environment, wiping out species that had thrived for millions of years. Yet even in this devastation lay the seeds of renewal. The few survivors carried the genetic blueprints for what would come next, adapting to a planet that had been reset by catastrophe. From these survivors emerged the creatures that would dominate the Mesozoic, the dinosaurs, the pterosaurs, and eventually the ancestors of mammals. It closed a chapter filled with creativity, innovation, and bold evolutionary leaps, and opened the door to a new age of giants and wonders. The Paleozoic ended in fire and silence, but from its ashes, the story of life continued, more complex and enduring than ever. Early coral reefs during the Paleozoic era. Coral reefs emerged as one of the most important ecosystems in the seas, providing shelter and food for a growing diversity of marine life. These reefs were built by primitive corals and stromatoporoids, creating complex structures that offered habitats for trilobites, brachiopods, and mollusks. Reefs were hotspots of biodiversity, where predator and prey coexisted in delicate balance. They expanded during the Ordovician and Silurian periods, flourishing in warm, shallow waters near the equator. As reefs grew larger, they influenced the chemistry of surrounding waters and stabilized sediments, allowing more life to thrive. They became arenas for evolutionary innovation as species adapted to live in, on, and around the reef structures. The reef ecosystem were highly sensitive to environmental changes, and mass extinctions would periodically disrupt their growth. Yet the resilience of these communities ensured their persistence throughout the Paleozoic. These early reefs laid the foundation for later coral systems that continue to shape oceans today. They were the first architectural marvels of marine life, demonstrating the power of cooperation, adaptation, and evolutionary experimentation. Trilobites, masters of the seafloor trilobites, were among the most iconic creatures of the Paleozoic era, appearing in the Cambrian and thriving until the end of the Permian. These arthropods were highly diverse, with thousands of species occupying nearly every marine niche. Some were burrowers, plowing through sediments for food, while others were swimmers or predators, hunting smaller organisms. Their hard exoskeletons provided protection and support, allowing them to develop a wide range of forms and behaviors. Trilobites evolved complex eyes capable of detecting movement and light in the dim Paleozoic seas. They were highly adaptable, surviving numerous environmental changes and mass extinctions, although ultimately the Permian extinction ended their long reign. Fossils of trilobites provide a remarkable record of evolution, showing subtle changes over millions of years. They serve as a window into the ecosystems of ancient oceans, revealing predator-prey dynamics and ecological interactions. Trilobites were more than mere survivors. They were pioneers of marine innovation. Their diversity, adaptability, and ecological success made them a defining presence in the Paleozoic oceans. a symbol of the era's creativity and complexity. Jod. Fish revolution. The Silurian and Devonian periods saw a revolution in marine vertebrates with the appearance of jawed fish. These creatures represented a major evolutionary leap, as jaws allowed more effective feeding strategies and opened new ecological opportunities. Placoderms, with armored heads and powerful jaws, became formidable predators in shallow seas. Sharks also appeared, sleek and efficient hunters, setting the stage for future dominance in oceans. Jawed fish diversified rapidly, with lobe-finned fish developing muscular fins that would eventually allow the first vertebrates to explore land. The evolution of jaws transformed ecosystems as predation became more sophisticated and food chains grew more complex. Fish colonized different depths, habitats, and environments, experimenting with size, shape, and hunting strategies. These innovations reshaped marine ecosystems, driving evolutionary arms races between predator and prey. Jawed fish also represent the first steps toward amphibians, reptiles, and ultimately mammals, linking the seas to terrestrial life. The rise of jawed fish was a turning point in vertebrate evolution, demonstrating the power of adaptation and innovation in shaping life's trajectory. Primitive forests take root. As the Paleozoic progressed, the first true forests began to take root, covering continents and creating complex terrestrial ecosystems. Early trees, like Archaeopteris, developed woody trunks and branching limbs, enabling them to grow tall and dominate landscapes. Ferns, horsetails, and lycopods filled the understory, creating dense vegetation that supported a variety of arthropods and amphibians. These forests stabilized soils, prevented erosion, and contributed organic material to rivers, influencing the chemistry of oceans. The spread of plants released oxygen, enriching the atmosphere and facilitating the evolution of larger, more active animals. Forests also provided shelter and food, allowing insects to diversify and early vertebrates to explore terrestrial habitats. Carboniferous forests were swampy and humid, creating environments that promoted gigantism in insects and amphibians. Floods, wildfires, and changing water levels shaped these dynamic ecosystems, forcing life to adapt. These forests were the first large-scale terrestrial habitats, transforming the land from barren landscapes to vibrant ecosystems. They also set the stage for coal formation, leaving a legacy that still fuels human civilization today. Arthropods, conker land insects, and other arthropods were among the first animals to conquer land, thriving alongside early plants and creating complex terrestrial ecosystems. Millipedes, scorpions, and early spiders explored forests and swamps, feeding on decaying plant matter and smaller organisms. Atmospheric oxygen was at an all-time high during the Carboniferous, enabling these creatures to grow to enormous sizes and dominate their environments. Arthropods developed a variety of adaptations to prevent desiccation, from waxy exoskeletons to behavioral strategies that kept them near water. They played essential roles in food webs, acting as herbivores, predators, and prey for amphibians and early reptiles. Their success on land demonstrates the evolutionary advantage of small size, mobility, and exoskeletal protection. The presence of diverse arthropod communities also influenced plant evolution, as feeding and pollination interactions began to shape vegetation. These pioneering terrestrial animals laid the foundation for the modern insects and arachnids that dominate today. Arthropods' conquest of land represents one of the most successful and enduring evolutionary experiments in Earth's history. Amphibians flourished during the late Paleozoic, filling nearly every ecological niche in swampy and forested environments. These early tetrapods descended from lobe-finned fish and retained strong ties to water for reproduction. Their moist skin enabled cutaneous respiration, allowing them to absorb oxygen while navigating damp landscapes. Amphibians ranged from small insectivores to massive carnivorous forms capable of preying on smaller vertebrates. They were central players in carboniferous ecosystems, interacting with arthropods, fish, and early reptiles. These animals showcased a remarkable diversity in body shapes, sizes, and behaviors, reflecting the variety of habitats they occupied. Some developed elongated bodies for swimming, while others evolved limbs suited for terrestrial locomotion. Amphibians were both predators and prey, influencing evolutionary pressures on surrounding species. Their adaptability allowed them to dominate for millions of years, bridging the gap between aquatic and fully terrestrial life early. Reptile evolution. Reptiles emerged during the late Paleozoic as the first vertebrates fully freed from dependence on water. The evolution of the amniotic egg was critical, allowing reproduction in dry environments and opening vast new ecological opportunities. Reptiles developed scaly skin to retain moisture and stronger limbs for efficient terrestrial locomotion. They diversified into a range of forms, from small insectivores to early carnivorous predators, experimenting with diet, size, and behavior. Reptiles were less restricted than amphibians, enabling them to colonize arid regions, deserts, and uplands. This evolutionary leap set the stage for the Mesozoic dominance of dinosaurs and other reptiles. Reptiles competed with amphibians for resources and gradually became the most successful vertebrates on land. Their adaptability demonstrates the power of key evolutionary innovations, such as the amniotic egg and keratinized skin. Early reptiles represent a turning point in vertebrate history, establishing the foundation for future terrestrial ecosystems, glaciations, and climate. Changed. The late Paleozoic was marked by dramatic climate shifts, including glaciations that reshaped continents and ecosystems. Ice sheets formed in southern Gondwana, lowering sea levels and exposing continental shelves, disrupting marine habitats. Cooling temperatures forced species to adapt or face extinction, reshaping evolutionary trajectories. These glacial periods also influenced ocean circulation, nutrient availability, and atmospheric composition, affecting life across the planet. Meanwhile, tropical regions remained warm and humid, supporting dense forests and diverse fauna. Fluctuating climates created a dynamic and challenging world, fostering innovation and resilience among species. Plants and animals evolved to survive extremes, from arid interiors to frozen margins. Climate-driven migrations and extinctions influenced the composition of ecosystems, allowing some groups to thrive while others disappeared. These environmental pressures prepared the stage for the mass extinctions that would end the Paleozoic era. Climate change during this era demonstrates that life's evolution is inseparable from planetary forces. Permian catastrophe, the final chapter of the Paleozoic, was dominated by the Permian-Triassic extinction, the deadliest event in Earth's history. Volcanic eruptions released massive quantities of greenhouse gases, triggering extreme warming, ocean acidification, and widespread habitat loss. Marine species, including trilobites, brachiopods, and corals, faced near-total collapse on land. Amphibians and reptiles were devastated, with ecosystems left largely barren. The event reshaped evolutionary pathways, eliminating dominant species and giving rise to new lineages in the Mesozoic. Survival favored adaptability, resilience, and small populations able to endure extreme conditions. While catastrophic, this event cleared ecological niches, allowing new forms of life to emerge and diversify in the subsequent era. The Permian catastrophe underscores the fragility of life and the transformative power of extinction in shaping Earth's evolutionary history. From destruction came renewal, and the legacy of the Paleozoic endured in the survivors that paved the way for future life. The first reef ecosystems reefs became the bustling cities of the Paleozoic seas, built by corals and stromatoporoids, and teeming with life unlike anything seen before. These structures offered shelter to trilobites, brachiopods, mollusks, and early fish, creating intricate food webs. The first reef systems were small by modern standards, but highly dynamic, with species evolving to occupy specific niches. Predators prowled among the coral branches, while herbivores grazed on algae and detritus. The complexity of these ecosystems spurred evolutionary innovation as survival demanded new strategies, body forms, and defenses. Reefs influenced water chemistry, stabilized sediments, and acted as nurseries for countless marine species. Their expansion throughout the Ordovician and Silurian periods marked one of the most important ecological transformations of the Paleozoic. Even after mass extinctions, reefs recovered and continued to shape the oceans. Fossilized reefs provide modern scientists with a window into the structure, diversity, and dynamics of ancient marine life. In essence, reefs were the first large-scale, architecturally complex habitats, demonstrating the ingenuity of life during the Paleozoic trilobite adaptations. Trilobites were masters of survival, exhibiting incredible diversity and adaptability. Throughout the Paleozoic era, their segmented bodies allowed for flexibility, while hard exoskeletons offered protection against predators. Trilobites developed compound eyes capable of detecting movement and light, an advanced sensory adaptation for navigating the ocean floor. Some were burrowers, plowing through sediments for food, while others were free swimmers, hunting smaller prey. Trilobite morphology varied dramatically, reflecting specialized lifestyles, feeding strategies, and ecological roles. They thrived in shallow seas, coral reefs, and deeper waters, demonstrating a remarkable range of adaptability. Trilobite fossils reveal a history of evolutionary experimentation, from spines and horns to highly complex eye structures. They survived multiple environmental changes and minor extinctions before finally succumbing to the Permian mass extinction. Their success highlights the importance of adaptability, specialization, and resilience in evolution. As one of the most recognizable Paleozoic animals, trilobites exemplify the ingenuity of early marine life and the rich diversity that characterized ancient oceans. Emergence of jawed vertebrates. The evolution of jawed fish during the Silurian and Devonian periods revolutionized marine ecosystems. Jaws allowed these animals to capture prey efficiently, opening new ecological niches and creating complex predator-prey dynamics. Placoderms, armored with protective plates, became dominant predators, while early sharks emerged as sleek and agile hunters. Jawed fish diversified rapidly, with adaptations in fins, scales, and body shapes, reflecting ecological specialization. Lobe-finned fish developed muscular fins capable of supporting weight, a precursor to vertebrates venturing onto land. This evolutionary innovation transformed food webs, increasing competition and driving further diversification. By experimenting with hunting strategies and habitats, jawed vertebrates laid the groundwork for amphibians and reptiles. The appearance of jaws marks a critical turning point in the history of vertebrate evolution, linking marine life to terrestrial expansion. The success of these creatures demonstrates how structural innovation can dramatically reshape ecosystems and evolutionary trajectories. Colonization of land by plants. Plants began modestly in the Silurian but transformed landscapes and atmospheres. Over millions of years, small mosses and liverworts stabilized soils, while vascular plants developed roots and stems, allowing them to grow taller and dominate terrestrial habitats. By the Devonian, forests were forming, with primitive trees and ferns covering continents. These plants released oxygen, altered carbon dioxide levels, and shaped the climate. Dense vegetation created habitats for insects, arthropods, and amphibians, forming the first complex terrestrial ecosystems. Forests moderated water cycles, preventing erosion and providing organic material for rivers and soils. Plant colonization also influenced sedimentation, helping to create fertile environments that supported further life expansion. Over time, plant diversity increased dramatically, including club mosses, horsetails, and early seed plants. The conquest of land by plants was a monumental evolutionary leap, fundamentally changing the Earth and enabling the rise of terrestrial animal life. It laid the foundation for ecosystems that continue to sustain life today. Carboniferous swamps. The Carboniferous period was dominated by lush, humid swamp forests that stretched across continents. Giant lycopods, ferns, and horsetails formed dense vegetation, creating ideal habitats for amphibians, insects, and early reptiles. These swamps contributed to massive coal deposits that endure today, evidence of the scale and productivity of these ecosystems. High atmospheric oxygen allowed arthropods to grow to enormous sizes, with dragonflies and millipedes reaching dimensions far beyond modern analogs. Amphibians thrived in these humid environments, hunting insects and smaller vertebrates. Swamps were dynamic, shaped by floods, seasonal changes, and occasional wildfires, forcing life to adapt to fluctuating conditions. These ecosystems were hotspots of biodiversity, combining aquatic and terrestrial life in close interaction. Rivers, lakes, and wetlands interwove with forests, creating interconnected habitats. The Carboniferous swamps represent a unique chapter in Earth's history, where environmental abundance and atmospheric richness allowed life to flourish in ways that would never be repeated. Giant insects. One of the most extraordinary features of the Paleozoic was the gigantism of insects, enabled by high oxygen levels in the Carboniferous atmosphere. Dragonflies with wingspans of over 2 feet soared above forests, while millipedes grew several feet long, dominating the undergrowth. Scorpions and early arachnids were abundant, preying on smaller insects and contributing to complex food webs. Oxygen-rich air allowed insects to sustain large bodies, fueling metabolic activity and enabling extended flight. These enormous arthropods interacted with plants, pollinating and feeding on vegetation, shaping the ecosystems around them. Predatory amphibians and early reptiles competed with giant insects, creating a dynamic interplay of life on land. Fossil evidence of these creatures reveals an ancient world strikingly different from today. With unusual proportions and formidable ecological roles, their size and abundance highlight the influence of atmospheric conditions on evolutionary outcomes. Giant insects of the Paleozoic remain iconic examples of the era's ecological uniqueness and evolutionary experimentation. Amphibians. Amphibians dominated Carboniferous wetlands and forests, showcasing remarkable diversity in size, form, and behavior. Descended from lobe-finned fish, they retained strong ties to water for reproduction, but adapted to terrestrial habitats for feeding and movement. Some species were small insectivores, while others grew into massive predators, hunting smaller vertebrates and invertebrates. Moist skin allowed oxygen absorption, and strong limbs enabled efficient navigation of swampy terrain. Amphibians filled multiple ecological niches, influencing the evolution of plants, insects, and other vertebrates. Their success demonstrates how adaptation to both land and water can provide evolutionary advantages. As both predators and prey, amphibians shaped the structure of early terrestrial food webs. Their diversity and abundance during the Carboniferous illustrate the complexity of Paleozoic ecosystems. Amphibians were crucial bridges between aquatic and terrestrial life, enabling the continued expansion of life onto land. Early reptilian innovations. Reptiles emerged in the late Paleozoic as pioneering vertebrates capable of thriving in drier environments. The evolution of the amniotic egg freed them from dependence on water for reproduction. Scaly skin reduced water loss, and stronger limbs improved mobility across varied landscapes. Reptiles diversified into carnivorous hunters and herbivorous grazers, occupying niches unavailable to amphibians. These adaptations allowed them to colonize deserts, uplands, and floodplains. Reptiles competed with amphibians, gradually becoming dominant terrestrial vertebrates. Their innovations paved the way for future Mesozoic dinosaurs and mammals. Reptiles demonstrated the power of structural and reproductive adaptations in enabling life to explore new habitats. Their rise reflects a pivotal transition in Paleozoic ecosystems, where terrestrial life began to evolve independently of aquatic constraints. Permian climate and extinction. The Permian period was marked by dramatic climatic shifts, from humid forests to arid interiors, as Pangaea assembled. Massive volcanic activity released greenhouse gases, warming the atmosphere and altering ocean chemistry. Species faced increasingly extreme conditions, including droughts, temperature fluctuations, and oxygen depletion in oceans. These pressures culminated in the Permian-Triassic extinction, the deadliest in Earth's history, eliminating the majority of marine and terrestrial species. Coral reefs, trilobites, and many amphibians vanished, reshaping ecosystems globally. The extinction cleared ecological niches for future Mesozoic lineages, illustrating the dual nature of catastrophe and opportunity in evolution. Life that survived adapted to new conditions, leading to innovative forms and behaviors. The Permian extinction highlights the interconnectedness of climate, geology, and life. It demonstrates that survival depends on flexibility, resilience, and the ability to exploit emerging opportunities in a rapidly changing world. Early marine predators, the Paleozoic seas, were arenas of evolutionary innovation where predators shaped the course of marine life. Large nautiloids and early sharks roamed the oceans, hunting trilobites, brachiopods, and smaller fish. Placoderms, armored-jawed fish, became apex predators of their time, using powerful jaws and bony plates to dominate shallow seas. Predation drove evolutionary arms races, forcing prey species to develop shells, spines, and evasive behaviors. Coral reefs and seafloor habitats provided shelter, allowing prey to escape predators and diversify. The interactions between predators and prey created dynamic food webs, fueling biodiversity across multiple ecological levels. Over millions of years, these marine ecosystems became increasingly complex, reflecting both cooperation and competition. Predator adaptations influenced swimming efficiency, body armor, and sensory systems in both predator and prey. The rise of large marine predators during the Paleozoic set patterns that would continue through the Mesozoic and beyond. These early hunters exemplified the relentless drive of evolution, where survival depended on speed, strength, and cunning. Stromatoporoid builders, stromatods, were vital architects of Paleozoic reefs, constructing massive calcareous structures that supported diverse marine communities. These sponge-like organisms laid the foundation for corals, brachiopods, mollusks, and fish to thrive. Reef construction altered local currents, stabilized sediments, and created microhabitats that encouraged specialization among marine organisms. Stromatoporoids were resilient to minor environmental changes, but vulnerable during mass extinctions, demonstrating the delicate balance of ecosystems. Their growth patterns, preserved in fossils, reveal the pace and scale of reef development over millions of years. By engineering these habitats, stromatoporoids indirectly influenced predator-prey dynamics, resource distribution, and species interactions. The presence of stromatoporoids highlights the critical role of ecosystem engineers in shaping biodiversity. These organisms exemplify how even sessile life forms can impact global evolutionary trajectories. Stromatoporoids' contributions to Paleozoic marine ecosystems laid the groundwork for reef systems that persist today. The Age of Fishius, the Devonian period, earned the title Age of Fishes due to the remarkable diversification and abundance of vertebrates in the oceans. Jowed fish, including placoderms, early sharks, and lobe-finned species, dominated the seas and explored new ecological niches. Lobe-finned fish with muscular fins paved the way for the first tetrapods to venture onto land. Fish evolved varied body sizes, feeding strategies, and behaviors, creating intricate predator-prey relationships. Coral reefs, seafloors, and shallow waters provided habitats for this burgeoning diversity. Fish interactions influenced evolution across the food web, from small invertebrates to top predators. The Devonian oceans were highly dynamic, with evolutionary pressures driving rapid adaptation and innovation. Vertebrate success during this period set the stage for amphibians and reptiles, bridging the marine and terrestrial worlds. Fossil evidence shows complex communities with clear ecological hierarchies. The age of fishes represents one of the most important chapters in Paleozoic life, demonstrating the transformative power of vertebrate evolution. Vascular plants spread during the Silurian and Devonian. Vascular plants revolutionized terrestrial landscapes, enabling taller growth and more efficient water transport. Roots stabilized soils, allowing rivers and floodplains to develop fertile sediment layers. Leaves and stems facilitated photosynthesis on a larger scale, increasing oxygen production and reducing carbon dioxide levels. These changes influenced global climate and atmospheric composition, shaping habitats for future life. Dense vegetation provided food, shelter, and microclimates for arthropods, amphibians, and early reptiles. Forests became complex ecosystems with multiple layers, from canopy to undergrowth. Plants also influenced sedimentation, soil formation, and river chemistry, affecting downstream marine environments. The spread of vascular plants created feedback loops, linking terrestrial and marine ecosystems in profound ways. Over millions of years, plant evolution transformed barren lands into thriving green landscapes. These developments laid the groundwork for the extensive forests of the Carboniferous and the eventual rise of seed plants. Vascular plants' colonization of land remains a pivotal event in Earth's evolutionary history. Swamp-dwelling amphibians. Carboniferous swamps were dominated by amphibians, which exploited wet, humid environments to hunt and reproduce. Amphibians ranged from small insectivores to giant carnivores capable of preying on other vertebrates. Moist skin enabled respiration, while strong limbs allowed movement through dense vegetation and shallow water. Amphibians were central to complex food webs, interacting with insects, arthropods, fish, and early reptiles. Their reproductive reliance on water kept them tied to swamps. Yet their adaptability allowed them to occupy diverse ecological niches. Some species developed elongated bodies for swimming, while others evolved limbs suitable for terrestrial locomotion. Fossils reveal a rich diversity of form and behavior, reflecting the dynamic nature of Carboniferous ecosystems. Amphibians' dominance exemplifies the evolutionary potential of transitional life forms, bridging aquatic and terrestrial habitats. These creatures thrived for tens of millions of years, influencing the evolution of surrounding species. Swamp-dwelling amphibians were both predators and prey, integral to the functioning of early Paleozoic forests. Insect megafauna. High oxygen levels during the Carboniferous allowed insects to grow to enormous sizes, reshaping terrestrial ecosystems. Dragonflies with wingspans exceeding 2 feet patrolled the skies. Scorpions, early spiders, and other arthropods were abundant and diverse, filling multiple ecological niches. These giant insects were both hunters and grazers, influencing plant evolution and shaping food webs. Predatory amphibians and early reptiles competed with insects, creating intricate ecological interactions. Fossils indicate adaptations for flight, predation, and survival in dense forests. Oxygen-rich air facilitated sustained activity, enabling larger body sizes and higher metabolic rates. Insect success during this period illustrates how environmental conditions can influence evolutionary trajectories. Their gigantism is unique in Earth's history, never again replicated at such scale. Carboniferous insect megafauna highlight the extraordinary possibilities of life under favorable atmospheric conditions. Reptilian pioneers reptiles emerged in the late Paleozoic as pioneering terrestrial vertebrates, freed from dependence on water. The amniotic egg allowed reproduction in arid regions, while scaly skin minimized water loss. Reptiles diversified into carnivores, herbivores, and opportunists, occupying niches unavailable to amphibians. Stronger limbs enabled efficient locomotion. Across varied terrain, they spread into deserts, floodplains, and uplands, demonstrating the adaptive power of structural and reproductive innovations. Reptilian success foreshadowed the Mesozoic dominance of dinosaurs. These early pioneers showcased evolutionary creativity and versatility, thriving in challenging habitats. Fossil evidence highlights diversity in body shape, size, and behavior. Reptiles' emergence reflects a turning point in terrestrial ecosystems, marking a shift toward independence from aquatic reliance. Permian environmental stress. The Permian period experienced extreme environmental changes, including aridification, volcanism, and fluctuating climates. Ice sheets in southern Gondwana altered sea levels, disrupting marine and coastal ecosystems. Volcanic eruptions released greenhouse gases, raising global temperatures and causing acidification in oceans. Terrestrial habitats faced droughts, desertification, and shifts in vegetation patterns. These pressures contributed to widespread extinctions, affecting both marine and terrestrial species. Ecosystems became fragmented, forcing species to adapt, migrate, or perish. Permian environmental stress set the stage for the End-Permian extinction, the most severe biotic crisis in Earth's history. Surviving species carried the potential to seed new lineages in the Mesozoic. The period demonstrates the profound impact of planetary forces on life's evolution. The Great Dying, the end of the Paleozoic, was marked by the Permian-Triassic extinction, or the Great Dying, which eliminated over 90% of marine species and a majority of terrestrial life. Volcanism, climate chaos, ocean anoxia, and acidification combined to create catastrophic conditions. Trilobites, many corals, and dominant amphibians vanished, reshaping global ecosystems. Reptiles and a few hardy species survived, carrying forward the genetic legacy of the Paleozoic. Ecological niches emptied, allowing new lineages to emerge in the Mesozoic. This event demonstrates the duality of extinction, devastation paired with evolutionary opportunity. Life's resilience became evident, paving the way for the rise of dinosaurs, mammals, and other Mesozoic dominants. The Great Dying remains the most dramatic example of planetary forces altering life's trajectory. From catastrophe came renewal, completing the Paleozoic chapter of Earth's history and opening the door to a new era of evolution. Cambrian biodiversity. The Cambrian period marked a dramatic explosion of life as marine ecosystems became rich with unprecedented diversity. Tiny organisms evolved hard shells, exoskeletons, and specialized appendages, enabling a variety of feeding and defensive strategies. Trilobites scuttled across seafloors, while sponges, worms, and early mollusks colonized every available niche. Predation emerged as a driving force, pushing species to innovate rapidly, resulting in remarkable morphological variety. The development of eyes, segmented bodies, and jointed limbs allowed creatures to navigate, hunt, and survive in complex environments. Plankton proliferated, providing food for larger organisms and fueling the growth of food chains. Coral-like organisms began forming rudimentary reefs, creating habitats that supported more species. Ecosystem complexity increased, with interdependent relationships shaping survival strategies. The Cambrian seas were both chaotic and orderly, with evolutionary innovation occurring at breakneck speed. This period laid the foundation for the entire Paleozoic, proving that life could diversify explosively when conditions permitted. Ordovician ocean expansion. The Ordovician period saw the proliferation of shallow seas covering much of the continents, fostering diverse marine life. Brachiopods, bryozoans, and mollusks thrived, constructing extensive communities along continental shelves. Early vertebrates, such as jawless fish, began exploring new ecological roles. Coral-like organisms contributed to reef expansion, providing shelter and resources for smaller creatures. Predation intensified, with nautiloids and other mobile hunters shaping prey adaptations. Plankton flourished, forming the base of intricate food webs that supported increasingly complex life forms. Environmental changes, including rising sea levels and shifting climates, created dynamic habitats. Shallow, warm seas were hotspots for evolutionary experimentation, with species radiating into specialized niches. Ordovician glaciation later triggered one of the earliest mass extinctions. The period emphasized the interplay between climate, sea level, and evolutionary innovation in shaping marine biodiversity. Silurian terrestrial beginnings. The Silurian period witnessed the first major steps of life onto land, as small vascular plants began colonizing dry habitats. These plants stabilized soils, allowing erosion control and nutrient accumulation for future ecosystems, exploiting new niches and food sources. Shallow freshwater systems connected terrestrial and marine environments, facilitating species transitions. Coral reefs and marine habitats continued to expand, providing ecological continuity. Early jawed fish diversified in the seas, experimenting with feeding strategies and body plans. The Silurian atmosphere, rich in oxygen, supported the spread of life into terrestrial habitats. Fossils indicate a diversity of plant and arthropod interactions, from feeding to shelter creation. These developments set the stage for Devonian forests, amphibian emergence, and the eventual rise of reptiles. The Silurian represents a critical transitional period. bridging the marine-dominated early Paleozoic with a future increasingly shared between land and sea. Evolutionary experimentation during this era laid the groundwork for terrestrial ecosystems that would flourish in subsequent periods. Devonian rivers and lakes. The Devonian period was shaped by the spread of rivers, lakes, and freshwater systems, providing diverse habitats for emerging life. Lobe-finned fish, amphibians, and early invertebrates explored these waters, bridging aquatic and terrestrial ecosystems. Freshwater habitats fostered rapid evolution, allowing species to adapt to variable environments. Vegetation along riverbanks stabilized soils and influenced water chemistry, promoting nutrient cycling. Predators, including placoderms and early sharks, patrolled these waters, influencing prey behaviors and morphologies. Sedimentation patterns preserved rich fossil records, offering glimpses into the dynamics of Devonian ecosystems. Amphibians began experimenting with life on land, using rivers and lakes as breeding and feeding grounds. Plant roots penetrated soils, creating habitats for arthropods and small vertebrates. Seasonal changes in freshwater systems drove adaptation, fostering resilience and versatility in species, demonstrating the interconnectedness of terrestrial and aquatic ecosystems. These habitats were critical in shaping evolutionary pathways that would dominate the late Paleozoic Carboniferous rainforests. Carboniferous rainforests covered vast regions with towering lycopods, ferns, and horsetails, forming dense, humid ecosystems. Amphibians thrived in swampy undergrowth, preying on insects and smaller vertebrates. Giant insects patrolled the canopy and forest floor, exploiting oxygen-rich conditions to achieve extraordinary sizes. Forests moderated the climate, stabilizing humidity and influencing local water cycles. Decomposing plant material enriched soils, contributing to coal formation and long-term carbon storage. Predation and competition within forests fostered complex food webs involving arthropods, amphibians, and emerging reptiles. Seasonal flooding and wildfires created dynamic environments, challenging species to adapt or perish. Canopy layers, understory vegetation, and swampy wetlands provided diverse habitats for a multitude of species. Forest expansion altered atmospheric oxygen and carbon dioxide levels, affecting global climate. Carboniferous rainforests represented a pinnacle of Paleozoic terrestrial ecosystems, combining density, diversity, and productivity on a scale unmatched until later geological periods. Amphibian giants. Amphibians of the Carboniferous reached remarkable sizes, dominating swampy ecosystems as apex predators and herbivores alike. Some species grew several meters in length, hunting insects, smaller amphibians, and fish. Their moist skin allowed cutaneous respiration, and strong limbs enabled movement through dense vegetation and shallow waters. These giants influenced ecosystem structure, regulating prey populations and competing with other predators. Fossil evidence reveals specialized adaptations, including elongated bodies, muscular limbs, and powerful jaws. Amphibians were integral to Carboniferous food webs, interacting with arthropods, fish, and early reptiles. High oxygen levels supported their metabolic demands and growth, facilitating gigantism. These amphibians exemplify how environmental conditions and evolutionary potential combined to produce extraordinary life forms. Their success reflects the adaptability and resilience of vertebrates during the Paleozoic. Reptiles rise. Late Paleozoic reptiles emerged as pioneers, exploiting terrestrial habitats beyond the reach of amphibians. The amniotic egg allowed reproduction in arid environments, while scaly skin minimized water loss. Reptiles diversified into carnivores, herbivores, and generalists, filling niches left open by declining amphibian populations. Strong limbs and efficient locomotion enabled exploration of varied landscapes, from floodplains to deserts. Competition with amphibians spurred further specialization, reinforcing evolutionary innovation. Early reptiles set the stage for Mesozoic dominance by dinosaurs and other vertebrates. Fossils show a variety of body sizes, shapes, and ecological roles, illustrating adaptability and resilience. Reptiles' success during the late Paleozoic underscores the importance of key innovations in survival and expansion. Their rise demonstrates a turning point in vertebrate evolution, where life could fully escape dependence on aquatic habitats. Paleozoic reptiles represent the foundation for future terrestrial ecosystems. Permian landscapes. The Permian period saw dramatic environmental transformations, including the assembly of Pangaea, the formation of deserts, and fluctuating climates. Arid interiors replaced tropical wetlands, challenging amphibians and early reptiles alike. Volcanic activity released greenhouse gases, contributing to warming and acidification of oceans. Rivers, lakes, and remaining wetlands became critical refuges for surviving life. Vegetation patterns shifted, with seed plants and hardy trees adapting to drier conditions. Fauna faced selective pressures that favored versatility, endurance, and efficient water management. Predatory reptiles exploited new niches, while surviving amphibians retreated to humid areas. Ocean chemistry and sedimentation reflected global climatic shifts affecting marine ecosystems. Permian landscapes were harsh, dynamic, and fragmented, driving rapid adaptation and shaping evolutionary outcomes. The stage was set for the catastrophic events that would close the Paleozoic era. Permian mass extinction. The Paleozoic concluded with the Permian-Triassic extinction, the most severe extinction event in Earth's history. Massive volcanism, global warming, ocean anoxia, and acidification wiped out over 90% of marine species and most terrestrial life. Coral reefs, trilobites, amphibians, and dominant fish species vanished, reshaping ecosystems forever. Reptiles, certain amphibians, and hardy invertebrates survived, carrying genetic blueprints for future lineages. Ecological niches emptied, allowing new evolutionary pathways to emerge in the Mesozoic. This extinction demonstrates the immense impact of geological and climatic forces on life. Surviving species evolved rapidly, adapting to altered conditions and seizing newly available habitats. The Permian-Triassic extinction serves as both a reminder of vulnerability and a catalyst for evolutionary innovation. Life endured, adapted, and set the stage for the age of dinosaurs. Completing the dramatic narrative of the Paleozoic era, Cambrian explosion. The Cambrian explosion was the defining moment of early Paleozoic life, when most major animal phyla first appeared in a relatively short geological period. Marine habitats filled with new forms, from trilobites and brachiopods to primitive mollusks and echinoderms. Hard shells and exoskeletons offered protection, while specialized appendages allowed movement, burrowing, and predation. Eyes evolved, providing vision for navigation and hunting, which accelerated the arms race between predator and prey. Reefs and seafloor structures created microhabitats that supported incredible biodiversity. Plankton proliferated, forming the base of increasingly complex food webs. Rapid diversification led to experimentation in body plans, feeding strategies, and ecological roles. Fossil beds from this period preserve astonishing detail, offering insights into early life's complexity. The Cambrian explosion illustrates how environmental stability and evolutionary potential can trigger unparalleled diversification. It set the stage for subsequent Paleozoic evolution and established the foundation for future ecosystems across oceans and continents. Ordovician biodiversity. During the Ordovician, life continued to expand in oceans as shallow seas covered much of the continents. Brachiopods, bryozoans, trilobites, and mollusks flourished, creating complex benthic communities. Early fish diversified, though jawless. They began to experiment with size, mobility, and feeding strategies. Reef-building organisms, including corals and stromatoporoids, expanded habitats, allowing species to occupy specialized niches. Plankton bloomed, enhancing food webs and supporting predator species like nautiloids. Environmental fluctuations, including rising and falling sea levels, spurred adaptation and migration. The Ordovician also experienced one of the earliest mass extinctions due to glaciation, eliminating many vulnerable species but allowing survivors to radiate. Life thrived in both stability and disruption, demonstrating resilience and flexibility. Ordovician biodiversity reflects the growing complexity of Paleozoic ecosystems, with intricate interactions between species and habitats. This period laid the ecological and evolutionary groundwork for the Silurian and Devonian. Silurian coral reefs. The Silurian seas saw the first extensive coral reefs constructed by corals, stromatoporoids, and algae. These reefs provided shelter, breeding grounds, and hunting areas for numerous invertebrates and fish. Complex architecture supported species diversification, allowing ecological niches to proliferate. Predation and competition within reefs drove morphological adaptations, from spines and shells to swimming strategies. Reef ecosystems influenced water chemistry and sediment stabilization, creating feedback loops that benefited both reef builders and associated fauna. Shallow, warm waters were ideal for reef expansion, while deeper waters served as refuges for more mobile species. Fossils reveal thriving communities with complex food webs, illustrating predator-prey dynamics and ecological balance. Reefs acted as evolutionary incubators, fostering specialization and diversity. Their proliferation during the Silurian marks a significant step in the complexity of marine ecosystems. These early reefs set the template for future reef evolution in the Devonian and beyond. Devonian forests transformed terrestrial landscapes, introducing trees like Archaeopteris with woody trunks and branching limbs. Early ferns, horsetails, and lycopods formed the undergrowth, creating layered ecosystems that sheltered arthropods and amphibians. Forests stabilized soils, enriched sediments, and influenced river and lake chemistry. Photosynthesis by dense vegetation increased atmospheric oxygen, supporting more active terrestrial animals. Forest expansion created microclimates, promoting insect diversification and amphibian adaptation to land. Seasonal flooding, storms, and wildfires shaped forest composition and drove evolutionary responses. These ecosystems connected terrestrial and freshwater habitats, facilitating amphibian evolution and the eventual rise of reptiles. Forests also contributed organic matter to soils and rivers, linking terrestrial and marine food webs. The Devonian marked a turning point where plants became dominant architects of Earth's surface, reshaping habitats and climate. Forests initiated a cascade of evolutionary changes that defined later Paleozoic life. Carboniferous, coal swamps. Carboniferous coal swamps were vast, humid wetlands dominated by towering lycopods, ferns, and horsetails. Dense vegetation created ideal habitats for amphibians, insects, and early reptiles. High oxygen levels enabled insects to achieve enormous sizes, while amphibians and reptiles exploited abundant food sources. Seasonal flooding and dynamic water levels forced species to adapt, promoting mobility, predation strategies, and reproductive specialization. Decomposing plants accumulated as peat, eventually forming coal deposits, evidence of these highly productive ecosystems. Swamps supported complex food webs, with arthropods as primary consumers and amphibians as apex predators. Predation and competition drove morphological and behavioral adaptation. Forest canopy layers, undergrowth, and wetlands created diverse ecological niches. These ecosystems were highly resilient yet sensitive to environmental change. Carboniferous coal swamps exemplify the interplay of climate, vegetation, and animal life, leaving a lasting geological and evolutionary legacy. Amphibian radiations. Amphibians radiated extensively during the Carboniferous, exploiting swamps, rivers, and forest floors. They exhibited remarkable diversity in size and morphology, from small insectivores to giant carnivores preying on fish and arthropods. Moist skin allowed respiration and survival in humid environments, while limbs facilitated swimming and terrestrial locomotion. Amphibians filled multiple ecological roles, influencing plant and insect evolution. Competition among species spurred adaptive innovations, including body elongation, limb modification, and dietary specialization. Fossil evidence reveals complex communities with predators, prey, and scavengers interacting dynamically. High oxygen levels supported larger body sizes and more active lifestyles. Amphibians' success demonstrates the importance of transitional adaptations in bridging aquatic and terrestrial ecosystems. They were both resilient survivors and drivers of evolutionary change. Their proliferation shaped Carboniferous ecosystems and paved the way for terrestrial vertebrate diversification early. Reptile diversification. Reptiles emerged in the late Paleozoic as versatile terrestrial vertebrates, freed from dependence on water by the amniotic egg. Scaly skin minimized water loss, while stronger limbs allowed exploration of dry environments and varied terrains. Reptiles diversified into herbivores, carnivores, and generalists, occupying niches previously dominated by amphibians. They thrived in deserts, floodplains, and uplands, demonstrating adaptability and resilience. Fossil evidence indicates varied body sizes, morphologies, and ecological roles. Reptiles' innovations laid the groundwork for Mesozoic dominance by dinosaurs and other vertebrates. Their expansion reshaped terrestrial ecosystems, influencing prey populations and predator-prey dynamics. Key adaptations, including reproductive independence and water retention, exemplify the role of structural innovation in evolutionary success. Early reptiles were pioneers, shaping the trajectory of terrestrial life. Their rise marked a major evolutionary shift in the late Paleozoic Permian climate. Permian landscapes experienced dramatic climate changes, from humid forests to expanding arid interiors. Continental assembly into Pangaea altered ocean currents, wind patterns, and precipitation, creating environmental stress on both marine and terrestrial species. Volcanic activity released greenhouse gases, causing global warming, ocean acidification, and hypoxia. Species faced extreme conditions that favored resilience, mobility, and adaptation to water scarcity. Vegetation shifted toward seed plants and drought-tolerant trees. Rivers and lakes became critical refuges for amphibians and reptiles. Climate fluctuations fragmented habitats, influencing migration, evolution, and extinction patterns. Marine ecosystems suffered oxygen depletion, while terrestrial ecosystems experienced desertification and habitat loss. Permian climate shifts set the stage for the end Permian mass extinction. This period illustrates the powerful influence of planetary forces on evolutionary pathways and survival outcomes. Permian Triassic extinction. The Paleozoic Era concluded with the Permian Triassic extinction, the most catastrophic event in Earth's history. Massive volcanic eruptions, global warming, ocean acidification, and anoxia caused the disappearance of over 90% of marine species and most terrestrial life. Trilobites, dominant corals, amphibians, and fish species vanished, reshaping ecosystems forever. Surviving reptiles, certain amphibians, and hardy invertebrates carried forward the genetic legacy of the Paleozoic. Emptied ecological niches allowed new lineages to emerge in the Mesozoic. The extinction underscores the interplay of geological, climatic, and ecological forces in determining life's fate. Life's resilience became evident as survivors adapted to new conditions, exploiting emerging habitats. This event marked the transition from the Paleozoic to the Mesozoic, closing a chapter of dramatic evolutionary experimentation. From catastrophe came opportunity, shaping the trajectory of life for millions of years to follow. Early shelled animals. The early Paleozoic saw the rise of animals with hard shells, a key innovation that allowed survival against predators. Trilobite, mollusks, and brachiopods developed exoskeletons that protected their soft bodies while enabling mobility. These adaptations fostered ecological specialization, from burrowers and grazers to free-swimming predators. Shell morphology varied dramatically, reflecting habitat, feeding, and defense strategies. Hard parts also contributed to fossil preservation, giving scientists rich insights into ancient ecosystems. Shelled animals played crucial roles in food webs, serving as prey for larger predators like nautiloids and early fish. Their diversification drove evolutionary arms races, prompting further innovation among both predators and prey. Shelled species also influenced sediment dynamics, forming reef structures and stabilizing seafloors. Over time, these adaptations enhanced survivability, enabling animals to colonize a variety of marine environments. Shelled animals exemplify how structural innovation drives ecological complexity. Evolution of Isida, development of eyes during the Paleozoic revolutionized animal behavior, enhancing survival and predation. Compound eyes in trilobites and other arthropods allowed detection of movement, light, and predators. Early fish evolved more advanced eyes for hunting in varied aquatic environments. From coordinated hunting to evasive maneuvers, predatory pressures accelerated eye evolution, leading to increasingly sophisticated visual systems. Eyes allowed animals to exploit new niches, improving navigation, feeding efficiency, and mate selection. Fossil evidence shows remarkable variation in eye structure, reflecting adaptation to depth, light levels, and predatory tactics. Enhanced vision transformed ecosystems, influencing predator-prey dynamics and species interactions. Evolution of sight represents a fundamental step in the sensory sophistication of life. By the end of the Paleozoic, eyes had become critical tools, shaping survival strategies across marine and terrestrial habitats. Cambrian predators' predation intensified during the Cambrian, driving evolutionary innovation across multiple lineages. Early predators included anomalocaridids, nautiloids, and other mobile hunters, which fed on trilobites, worms, and small-shelled animals. Predatory strategies influenced body forms, mobility, and sensory adaptations among prey species. Hard shells, spines, and burrowing behaviors emerged as defensive responses. This arms race created dynamic and complex ecosystems where survival depended on speed, stealth, and adaptability. Predators also shaped population structure, controlling prey numbers and promoting diversification. Reef structures provided hunting grounds and hiding spots, adding spatial complexity. Cambrian predators exemplify how selective pressures drive rapid evolutionary change. Their presence catalyzed biodiversity and morphological experimentation across early Paleozoic oceans. Predation became a central force, shaping ecological relationships and evolutionary pathways during this era. Ordovician radiation. The Ordovician period experienced a remarkable radiation of marine life, with species diversity reaching new heights. Trilobites, brachiopods, bryozoans, and mollusks expanded into multiple ecological niches. Reef ecosystems flourished, supporting complex food webs and sheltering numerous species. Early jawless fish experimented with locomotion, feeding, and body size. Plankton blooms provided energy for higher trophic levels, fueling ecosystem expansion. Environmental changes, including fluctuating sea levels, promoted migration and adaptation. The Ordovician radiation demonstrated resilience and innovation, with species evolving novel morphologies and behaviors. Predation pressures intensified, stimulating defensive adaptations among prey species. These evolutionary dynamics set a precedent for future diversification in the Silurian and Devonian. The period exemplifies how life can rapidly diversify. under favorable environmental conditions, creating rich, interconnected ecosystems. Ordovician radiation remains a cornerstone in understanding Paleozoic biodiversity. Silurian land animals. Silurian land colonization saw arthropods venture onto dry surfaces, exploiting plants for food and shelter. Millipedes, scorpions, and primitive insects established themselves as terrestrial pioneers. Their presence drove interactions with early vascular plants, creating novel ecological relationships. Predatory behaviors evolved as arthropods hunted smaller invertebrates, while herbivory influenced plant morphology. Shallow freshwater systems acted as corridors between marine and terrestrial habitats, facilitating further expansion. Fossil evidence shows adaptation to varied microclimates, with moisture retention, locomotion, and feeding strategies shaping survival. Land colonization set the stage for Devonian forests, amphibian evolution, and the rise of reptiles. Arthropods. Success highlights the interplay of structural innovation, environmental opportunity, and evolutionary pressure. Silurian land animals laid the foundation for terrestrial ecosystems that would become increasingly complex in later Paleozoic periods. Their pioneering role underscores the significance of early adaptation to non-marine habitats. Devonian fish. Diversity. The Devonian era saw unparalleled diversification of fish, earning it the title Age of Fishes. Jowd fish, placoderms, and early sharks explored predator and prey roles in oceans, rivers, and lakes. Lobe-finned fish developed muscular fins, prefiguring the first tetrapods. Fish evolved body shapes, scales, jaws, and teeth specialized for feeding, hunting, and defense. Reef systems and benthic environments provided habitats for ecological experimentation. Competition and predation drove rapid adaptation and niche specialization. Fossil evidence shows a wide array of innovation, including armored plates, streamlined bodies, and powerful jaws. Fish diversity influenced other marine organisms, shaping predator-prey dynamics and ecosystem complexity. This era set the evolutionary foundation for amphibians and reptiles. The Devonian demonstrates how environmental opportunity combined with structural innovation to drive vertebrate diversification. Fish evolution exemplifies the creative force of natural selection during the Paleozoic. Devonian forest evolution. Devonian forests emerged as dense, layered ecosystems dominated by early trees, ferns, and lycopods. Roots stabilized soils, enabling riverbanks and floodplains to thrive. Forests moderated local climates and created microhabitats for arthropods and amphibians. Photosynthesis increased oxygen levels, fueling larger body sizes and more active life on land. Seasonal flooding, storms, and fire events drove evolutionary pressures, shaping plant and animal adaptation. Forests enriched soils with organic matter, influencing terrestrial and aquatic nutrient cycles. Canopy layers and understory complexity promoted species diversification and ecological interactions. Forest evolution exemplifies the interplay between vegetation and terrestrial ecosystems. These habitats facilitated amphibian expansion and later reptilian innovation. Devonian forests were critical in linking atmospheric, terrestrial, and aquatic changes to evolutionary pathways. Their emergence marks a transformative phase in Earth's ecological history, Carboniferous faunal expansion. The Carboniferous period was characterized by a proliferation of amphibians, insects, and early reptiles in swampy, humid environments. Giant dragonflies, millipedes, and scorpions. Reptiles began experimenting with terrestrial niches, exploiting environments inaccessible to amphibians. Forests and wetlands provided food, shelter, and breeding grounds for a variety of species. Predation, competition, and environmental fluctuation drove evolutionary innovation. Swamps accumulated organic matter, eventually forming coal deposits, preserving a rich fossil record. Seasonal changes shaped behavior, reproductive strategies, and survival mechanisms. Food webs became increasingly complex, with herbivores, predators, and scavengers interacting dynamically. Carboniferous faunal expansion demonstrates how ecosystem productivity, atmospheric composition, and environmental stability influence biodiversity. This period highlights the interplay between climate, vegetation, and animal life in shaping evolutionary outcomes. Permian ecological shifts. The Permian period witnessed dramatic ecological changes as Pangaea assembled. Arid interiors expanded, and climates fluctuated. Deserts replaced swamps, and sea levels shifted, stressing both marine and terrestrial species. Volcanic activity released greenhouse gases, raising temperatures and altering ocean chemistry. Seed plants and drought-tolerant vegetation adapted to new conditions, while amphibians retreated to humid refuges. Reptiles exploited dry habitats, spreading across floodplains, uplands, and deserts. Marine ecosystems experienced hypoxia, acidification, and habitat fragmentation. Species faced selective pressures favoring resilience, mobility, and adaptation to environmental extremes. Predation, competition, and climate drove morphological and behavioral innovation. Permian ecological shifts set the stage for the end Permian mass extinction. Life responded with evolutionary experimentation, survival, and adaptation, reshaping global ecosystems. Reef ecosystem dynamics. Paleozoic reefs, built by stromatobroids, corals, and algae, formed hubs of marine biodiversity. These structures provided shelter, breeding grounds, and hunting zones for invertebrates and early fish. Predation and competition shaped the reef's ecological balance, influencing body forms and behaviors. Reefs altered local currents, stabilized sediments, and created microhabitats for specialized species. Complex food webs developed, including herbivores, filter feeders, and apex predators. Reef expansion contributed to ecological innovation and species diversification. Fossil evidence shows intricate community structures reflecting predator-prey interactions and symbioses. These ecosystems were highly productive and resilient, yet vulnerable to environmental disruption. Reefs exemplified evolutionary experimentation, facilitating morphological diversity and niche specialization. By the late Paleozoic, reefs were critical to marine life, shaping evolutionary trajectories for millions of years. Predator-prey arms races throughout the Paleozoic. Predator-prey interactions drove rapid evolutionary innovation. Trilobites, an early fish, evolved shells, spines, and speed to escape predation. Predators developed stronger jaws, agility, and sensory adaptations to capture elusive prey. These arms races produced morphological diversity, complex behaviors, and ecological specialization. Reefs, swamps, and forests became arenas for evolutionary competition. Fossils reveal scars, injuries, and adaptations as evidence of these interactions. Arms races influenced population dynamics, ecosystem structure, and survival strategies. Predation pressure encouraged experimentation in locomotion, defense, and hunting techniques. Over millions of years, these dynamics shaped species, composition, and ecosystem resilience. The Paleozoic demonstrates how interactions among organisms can drive diversification and adaptive success. Predator-prey relationships remain a central force in shaping life's complexity. Marine biodiversity peaks. Paleozoic oceans experienced multiple biodiversity peaks, particularly in the Ordovician, Devonian, and Carboniferous periods. Reef expansion, plankton proliferation, and ecological innovation fueled these surges. Trilobites, brachiopods, mollusks, and early fish diversified into numerous forms, occupying specialized niches. Plankton blooms supported food webs extending from microfauna to apex predators. Environmental stability, warm seas, and nutrient-rich waters facilitated high productivity. Fossils indicate interactions between species, from symbiosis to predation. Biodiversity peaks fostered resilience, allowing ecosystems to recover from perturbations. Complex habitats encouraged morphological and behavioral innovation. Marine biodiversity influenced sedimentation, reef building, and ocean chemistry. These periods demonstrate how environmental opportunity and evolutionary experimentation drive life's richness. Terrestrial arthropod expansion. Paleozoic land saw arthropods flourish, exploiting plants, detritus, and prey. Millipedes, scorpions, and early insects adapted to terrestrial life with moisture retention, locomotion, and feeding strategies. High atmospheric oxygen during the Carboniferous enabled gigantism, producing dragonflies, millipedes, and scorpions of extraordinary size. Arthropods shaped terrestrial ecosystems, influencing plant evolution and soil formation. Predation, competition, and reproduction drove adaptive innovation. Fossil evidence shows diverse ecological roles, including herbivores, predators, and scavengers. Arthropod expansion facilitated food web complexity, connecting terrestrial and freshwater habitats. These organisms were pioneers in colonizing land, bridging aquatic and terrestrial ecosystems. Terrestrial arthropods exemplify evolutionary versatility and environmental adaptability. Their proliferation left lasting ecological and evolutionary impacts on Paleozoic landscapes. Amphibian adaptations. Amphibians diversified during the Carboniferous and Permian, exploiting swamps, rivers, and forests. Morphological adaptations included elongated bodies, powerful limbs, and specialized jaws. Moist skin enabled respiration, while reproductive dependence on water influenced habitat selection. Amphibians filled multiple ecological roles, from insectivores to apex predators. Competition and predation drove behavioral and structural innovation. Fossil evidence reveals diversity in size, shape, and ecological niche. Amphibians linked aquatic and terrestrial ecosystems, influencing evolutionary trajectories of other species. Environmental changes, including fluctuating water levels and seasonal climates, shaped adaptation strategies. High oxygen levels supported activity and gigantism. Amphibian evolution illustrates transitional adaptations, bridging life in water and on land. Reptilian innovations, late Paleozoic reptiles, introduced evolutionary breakthroughs that allowed full terrestrial independence. The amniotic egg eliminated reliance on water for reproduction, while scaly skin minimized desiccation. Strong limbs and body support enabled exploration of deserts, uplands, and floodplains. Reptiles diversified into carnivores, herbivores, and omnivores, filling niches previously inaccessible to amphibians. Fossils show varied morphology, size, and adaptations for survival. Reptiles influenced predator-prey dynamics, ecosystem structure, and species evolution. Innovations in reproduction and physiology ensured resilience in arid conditions. These adaptations foreshadowed Mesozoic vertebrate dominance. Reptiles' emergence marked a critical turning point in terrestrial ecosystems. Their success demonstrates the power of structural and reproductive innovation in evolutionary history. Permian environmental stress. The Permian period experienced extreme environmental challenges, including aridification, climate swings, and volcanic activity. Large-scale continental assembly into Pangaea altered wind, rainfall, and ocean currents. Volcanic eruptions released greenhouse gases, raising global temperatures and altering ocean chemistry. Marine ecosystems faced hypoxia and acidification, while terrestrial habitats fragmented. Flora adapted to drier conditions, with seed plants dominating previously swampy regions. Fauna experienced selective pressures favoring resilience, water, conservation, and mobility. Predation and competition influenced survival strategies. Environmental stress set the stage for dramatic ecological shifts and mass extinction. Fossils show patterns of adaptation and decline among marine and terrestrial species. Permian conditions illustrate the profound impact of planetary processes on life, mass. Extinction consequences. The end Permian extinction reshaped Earth's ecosystems, eliminating most marine species and large terrestrial vertebrates, trilobites. Corals, dominant amphibians, and many fish vanished, leaving ecological niches empty. Reptiles, hardy amphibians, and invertebrates survived, providing the foundation for Mesozoic evolution. Ecosystems were simplified, and competition decreased temporarily, allowing surviving species to radiate. New habitats opened, prompting innovation and adaptive experimentation. Recovery took millions of years, demonstrating life's resilience. Fossil records reveal patterns of extinction, survival, and recodify. Mass extinction highlights the role of catastrophic events in directing evolutionary trajectories. Life responded by diversifying in novel ways, setting the stage for the rise of dinosaurs and modern vertebrates. The Permian Triassic event marks a dramatic transition in Earth's history. Paleozoic legacy. The Paleozoic Era left a profound legacy on Earth, shaping oceans, continents, and life itself. Reef structures, coal deposits, and fossil beds preserve the record of millions of years of evolution. Vascular plants transformed terrestrial landscapes. Amphibians and reptiles pioneered land colonization, and marine life achieved unprecedented diversity. Innovations in sensory systems, locomotion, and reproduction established patterns that persist today. The era demonstrated the interplay of environmental change, predation, and adaptation in driving evolution. Mass extinctions tested resilience, reshaping ecosystems and opening new evolutionary pathways. Paleozoic life laid the foundation for the Mesozoic, providing both survivors and opportunities. Its legacy is recorded in rocks, fossils, and the genetic blueprints of modern species. Understanding the Paleozoic illuminates life's capacity for innovation, adaptation, and survival. Transition to the Mesozoic. As the Paleozoic ended, Earth prepared for the Mesozoic with major environmental and evolutionary shifts. The Permian-Triassic extinction left ecosystems simplified yet full of opportunity for surviving lineages. Reptiles began to dominate terrestrial habitats, while new marine species emerged in post-extinction seas. Climate stabilization, continental drift, and evolving vegetation shaped habitats for the next era. Evolutionary innovation continued, with surviving amphibians, invertebrates, and plants adapting to altered conditions. Food webs restructured, predation intensified, and species radiated into empty niches. Fossil evidence shows a gradual recovery and diversification in both oceans and continents. The transition highlights the resilience of life in the face of catastrophic change. Paleozoic foundations enabled Mesozoic ecosystems to flourish, setting the stage for dinosaurs, mammals, and modern biota. Life's continuity underscores the enduring power of adaptation and evolutionary potential. Early marine ecosystems. The earliest Paleozoic oceans were teeming with life, yet simple compared to later periods. Dominated by small invertebrates like trilobites, brachiopods, and sponges. Microbial mats stabilized sediments, while early burrowing animals altered seafloor structures, creating niches for new species. Predation was beginning to emerge, spurring defensive adaptations like shells and spines. Soft-bodied organisms experimented with mobility and feeding strategies, expanding the range of ecological roles. Planktonic organisms formed the base of nascent food webs, supporting small predators and scavengers. Reefs were rudimentary but provided critical shelter and breeding spaces for invertebrates. Fossil evidence shows rapid experimentation in body forms and behaviors during this era. Ecosystem complexity increased as species interacted, competed, and coexisted in diverse ways. Early marine ecosystems set the stage for the Cambrian explosion, demonstrating how environmental opportunity can spark diversification. These foundational habitats were crucial for the evolution of complex life. Primitive plant colonization. The Silurian marked the rise of primitive plants on land, beginning the transformation of terrestrial landscapes. Small vascular plants, including mosses and early ferns, established themselves in moist environments along riverbanks and wetlands. Their root systems stabilized soil and facilitated nutrient cycling, altering local ecosystems. Plants provided habitats and food sources for pioneering arthropods, forming the first terrestrial food webs. Seasonal changes drove adaptation, with some species developing tolerance to drier periods. Early plant evolution influenced atmospheric oxygen and carbon dioxide, shaping global climate. Fossil evidence shows early diversification in leaf morphology, reproductive structures, and growth strategies. Plant colonization created new ecological niches, allowing subsequent evolution of terrestrial vertebrates. These early pioneers demonstrated how structural innovation and environmental opportunity drive ecosystem development. Primitive plants laid the groundwork for the expansive forests of the Devonian and Carboniferous. Freshwater habitat expansion. Devonian rivers, lakes, and wetlands became critical sites for species diversification. Lobe-finned fish and early amphibians explored these habitats, bridging aquatic and terrestrial life. Freshwater systems allowed experimentation in feeding, locomotion, and reproduction. Seasonal variation and water chemistry influenced adaptation strategies. Plants along waterways stabilized soils, provided shelter, and contributed to nutrient cycling. Predators like placoderms and early sharks patrolled rivers and lakes, shaping prey behavior. Freshwater ecosystems connected terrestrial and marine habitats, facilitating species migration and ecological interaction. Fossil evidence shows diverse communities thriving in these environments. Freshwater expansion exemplifies how ecological opportunity drives evolutionary innovation. These habitats were essential stepping stones for the colonization of land. Rivers and lakes fostered biodiversity, ecological complexity, and the emergence of new life forms. Reef builders and biodiversity. Silurian and Devonian reefs provided ecological hotspots for marine biodiversity. Stromatoporoids, corals, and algae constructed extensive reef structures, offering shelter, breeding grounds, and hunting areas. Predators and prey coexisted in intricate networks, shaping morphological and behavioral adaptation. Food webs became more complex, integrating herbivores, filter feeders, and apex predators. Fossils reveal interactions such as symbiosis, competition, and predator-prey dynamics. Reefs were centers of evolutionary experimentation, promoting diversification and specialization. Their productivity supported a wide range of marine organisms. Reefs exemplify how physical structures can drive ecological complexity. Reef ecosystems set templates for future reef systems in the Mesozoic and beyond. Arthropod innovation. Land-dwelling arthropods flourished in Paleozoic terrestrial ecosystems, exploiting plants and detritus as food sources. Millipedes, scorpions, and early insects evolved adaptations for moisture retention, locomotion, and feeding on diverse resources. Predation among arthropods led to defensive strategies, spurring morphological innovation like armor and appendage. Specialization. Giant insects arose during the Carboniferous, supported by high oxygen levels. Arthropods shaped soil composition, plant evolution, and ecosystem dynamics. Fossil evidence shows extensive diversity in size, behavior, and ecological role. Their expansion onto land bridged aquatic and terrestrial ecosystems, creating new food webs. They were both drivers and beneficiaries of ecosystem complexity. Paleozoic arthropods laid the foundation for the dominance of insects in later terrestrial ecosystems. Amphibians and terrestrial transition. Amphibians were central to the transition from water to land during the Devonian and Carboniferous adaptations. Like limbs, lungs, and cutaneous respiration allowed them to exploit swamps, rivers, and forests. Amphibians filled multiple ecological roles, from insectivores to apex predators. Competition and predation influenced morphology, size, and behavior. Reproduction tied to water limited some habitats, but terrestrial foraging expanded their ecological reach. Fossils revealed diversity in body shape, locomotion, and feeding strategies. Amphibians bridged aquatic and terrestrial ecosystems, shaping food webs and species interactions. Environmental fluctuations forced adaptability, promoting resilience. High oxygen levels supported larger sizes and more active lifestyles. Amphibians' success illustrates the importance of transitional adaptations in evolutionary history. Seed plant expansionalate Paleozoic ecosystems saw the rise of seed plants, replacing spore-based species in many regions. Seeds allowed reproduction in drier conditions, facilitating expansion into uplands and arid areas. Seed plants stabilized soils, enriched habitats, and influenced water cycles. Their growth created new ecological niches, sheltering arthropods and vertebrates. Forest composition diversified with layered canopies and undergrowth. Seasonal flooding, fires, and climate shifts shaped adaptation strategies. Fossil evidence indicates diversification in morphology, reproduction, and ecological role. Seed plants altered atmospheric composition and carbon cycles, affecting global climate. Their expansion provided resources and habitats that drove vertebrate evolution. Seed plants were critical for the adaptation of terrestrial ecosystems to increasingly arid environments. Vertebrate radiation, the Devonian and Carboniferous periods, witnessed the radiation of vertebrates, including fish, amphibians, and early reptiles. Lobe-finned fish explored freshwater systems and evolved features prefiguring tetrapods. Amphibians colonized swamps and forests, while early reptiles began exploiting arid habitats. Vertebrates diversified in morphology, feeding strategies, and ecological roles. Predation, competition, and environmental changes drove adaptive innovation. Fossil evidence shows specialized limbs, jaws, and sensory systems. Vertebrate radiation reshaped ecosystems, creating new food webs and interactions. High oxygen levels supported activity and gigantism. Vertebrates became increasingly dominant in both aquatic and terrestrial habitats. Their evolution illustrates the interplay between environmental opportunity and structural innovation. End Permian transformations. The Permian period concluded the Paleozoic with dramatic environmental and ecological transformations. Pangaea's assembly altered ocean currents, climates, and habitats. Deserts expanded, while volcanic activity released greenhouse gases, warming the planet and acidifying oceans. Marine ecosystems experienced hypoxia, and terrestrial habitats fragmented. Flora adapted to aridity, with seed plants dominating previously wet regions. Fauna faced selective pressures, favoring resilience, mobility, and adaptation to extreme conditions. Predation and competition influenced survival. Fossils, record patterns of adaptation, decline, and ecological restructuring. End Permian changes highlight the impact of planetary-scale processes on evolutionary trajectories and ecosystem survival.